Niels Bohr used the quantized energy concept of Planck and took the quantum of action concept from Einstein to describe the excited state hydrogen atom. He incorporated the hydrogen spectrum formula developed by Rydberg and Balmer. Analysis of this line of reasoning begins with the hydrogen gas discharge tube. This is a hydrogen-filled tube excited by 5,000 volts. 10 million electrons per second fly through the gas. They could reach 14% of light speed unobstructed. In reality, free electrons collide with hydrogen electrons, knocking them out of their orbits. Hydrogen atoms reassemble with ionic electrons in this electron-rich environment. This creates the pink hue. Individual frequencies are seen with a diffraction grating. Balmer noticed that the spectral lines appeared to be mathematically related. He used the find a formula to fit the data method to relate the visible lines. This empirical methodology is nicknamed F3D. Rydberg, 3 years later, used F3D to expand the formula to the non-visible ultraviolet and infrared lines. It is amazing how accurate this mathematical formula is. The visible spectra yield some clues as to what is going on. The strongest lines have wide separations and the weakest ones have narrow differences. This data suggests a ringing formation. The strong, widely separated lines appear to be overshoot. The closely spaced faint lines point to stability. This is not the direction that Bohr took. Bohr made the huge assumption that the lines represented energy transitions between fixed orbits based on energies defined by the Planck-Einstein relation. He concentrated on the strong lines. Here, we follow the Rydberg formula as it is transformed by Bohr into an orbital energy equation with wave numbers morphing into quantized radial orbits. The Rydberg constant was originally set using a data fit. Bohr used the electron's Coulomb force versus centripetal force orbital model to generate the Rydberg constant mathematically. The wave numbers set the orbits. The atomic electron orbits were quantized. This is the excited state atomic model. Here is a familiar pictograph showing quantized orbits and the strong line frequencies that place electrons into these fixed orbits. The orbits can be excited or relaxed with discrete jumps. The ground state is the innermost radius. The red line indicates an orbit transition from n equals 3 to n equals 2. Red line energy is determined by the Planck-Einstein relation E equals hf. At this point, we must sidebar and scrutinize an error that has supported quantum for over 100 years. It is the notion that an electron in circular orbit radiates. Quantum mechanics was understood to counteract this problem. Ironically, the circular orbit radiation assumption is caused by a misapplication of Larmore's charged particle radiation formula. Larmore could have, but failed to bring this misunderstanding to the attention of physicists forming the new atomic theory. The biggest error is the insertion of centripetal acceleration into the Larmore formula, where linear acceleration is exclusively required. The reasoning goes something like this, quote, making a Lorentz transformation to the rest frame of the point charge. This argument allowed the summation of linear and centripetal acceleration in the Larmore radiation formula. It should be noted that a particle in centripetal acceleration is not undergoing scalar velocity change. Its kinetic energy is not being altered. No external energy source is required. The notion of linear acceleration, with the reference point being perpendicular to that action, is academically understood in the more extensive Leinart-Weichert derivations. That said, the original logical error has never been challenged and corrected. There are many problems with the Bohr atom. Some are outlined here. The first is the overall model. The excited state model requires discrete orbits, prescribed by nature, with integer-related circular path lengths. It is a standing wave configuration, reminiscent of vibrations. Since the paths are perfectly circular, this characterization is very weak. Bohr did not consider any ionic activity in the model he adapted from the Rydberg formula. With 10 million electrons flowing through the gas discharge tube per second, hydrogen atoms are deconstructed as free electrons bombard orbiting electrons, knocking them off the atom. Atoms reassemble in this environment, creating the spectra. Every atom can accommodate ionic electrons. This is well known. In this electron-dense environment, it would be expected. Orbital reassembly with anionic electrons would also produce radiation. Bohr did not consider any other way to interpret the spectra. Bohr assumed that electrons jump from one discrete orbit to another based on energy differences dictated by the Planck-Einstein relation. He did not elaborate on how the electron in this orbit-changing dynamic generated a single wavelength. He completely ignored the dynamics implied by the Larmor formula for charged particle radiation. There is a real effect, which is light, and the theory is inadequate to the task of explaining it. Bohr proposed no dynamics for how an electron jumped between states. There would be variable acceleration in normal orbital transition dynamics. Radiation patterns would be expected to show this. The reasons that electrons change quantum states were not explained. Bohr did not interpret the variable intensities of the lines in the spectra. He could not explain why the low-frequency lines in the Balmer series were very bright and the high-frequency lines were barely visible. The red line had the smallest radial orbit jump, implying the smallest change in orbital energy transition, but it was the strongest one in the series. The faint blue lines had a much larger orbital energy difference. The only explanation later proffered was that the effect could be a consequence of the number of electrons undergoing the transitions in the sample. Enrico Fermi made an effort to assess those probabilities. The standing wave idea is a weak utilization of Planck's methodology. Why an integral number of wavelengths might be assumed to have any physical relevance is questionable. The orbit is not vibrating and has no fixed boundary condition. Even the slowest electron travels at approximately 1% of light speed, making quadrillions of orbits per second. There is no altitude maintenance dynamic at these velocities. With no excited state cutoff point, the spectra implied the existence of orbits far out from the nucleus. The liberties Einstein took in the photoelectric effect analysis were incorporated and expanded by Bohr, leading to an atomic description that violated classical physics principles of radiation production. They required numerous leaps of logic and selective ignorance of multiple experimental loose ends. Nevertheless, the spectral data allowed Bohr to make a case so mathematically compelling that it looked like an epiphany. He aggressively promoted his ideas. Scientists who should have been more discriminating were easily led. The only price was the selective abandonment of some classical theory. Even with all these problems, the model was expanded, further obscuring classical physics ideas, with formal mathematical treatment in wave equation theory.